Hey guys, your boy Chili here. Welcome back to ROM hacking. A lot has happened since the last episode, so let me fill you guys in. The first thing, the biggest thing, was I lost the entire project. All the work I did. Poof. Gone. All my apes gone. I'm gonna, spare you the entire story of it, but it was not good. And, after that, I spent a little time soul searching, and then I went and I rebuilt it all, built it all back, and built it back better than before. So I redid all the comments and all the routines that I had reverse engineered and all the structures and everything. And I had caught things that I missed before. This is a more detailed annotation of the code. And I'm not happy that I had to do it, but it's done now, and it is what it is. And now I have everything under Git control and backed up on GitHub, so I will be able to cover my butt a little better in that respect. I'd also lost my save game. I had to redo all the stuff I did there. But in doing that, I got a piece of equipment that I had missed before. This sword, I had forgotten to get it from a place. So yeah. And here's one thing. At the end of the last video, we had discovered some stuff about the gauntlets, right? We had discovered that equipping them and unequipping them, when we examined memory using the cheat functionality, we saw the value 81 hex appearing in memory, in a specific location in memory. Now let me show you something here. I'm looking at, this is the character sheet of Harambe at a specific offset. Let's put something in his inventory. Interesting. We just see the 8-1 appear in this location of the inventory when we inserted the gauntlets. Nice. Okay, so there's some relation there. What if I were to remove something from his inventory? Boom. Something went to 0. Then everything was shifted over. So we see 8-1, 4F, 5-2, 6D. If I were to put the sword back in here, we see a 5-1 coming over here. And I think now, at this point, everyone is pretty much clear on what's going on here. This order of bytes here exactly corresponds to the items in his inventory. Each item has its own unique identifier, single byte. Hex 81 is for gauntlets. 5-1 is for a sword. 5-2 is for a sword plus 1, etc., etc. And now that we know this, it is going to be a lot easier. This is a big piece of the puzzle. And I think some of you guys have even surmised that at the end of my last video from what I saw in comments. So you can see here when I redid the character sheet, I fleshed it out even more. So I added in the inventory that I discovered, those 8 slots, but I also added in a bunch of spell slots, ability slots, things for like gold, experience, and just generally there's more and it's better than it was before. Interesting thing is, okay, so we know that all these different inventory items have their own unique identifiers. It might be neat to chart them, to change the memory and see for every value what shows up. But then I realized, you know what? That work has already been done because people have done guides on save state hacking, and a quick check showed me that exactly corresponds to the values used in memory. So you see here 8-1, Gauntlets of Ogre Power. Let's go to 5-1. That's a sword. There you go. Again, is no easier than that. So, now one final thing I want to share with you. I had my suspicions about whether the magical weapons, the sword plus 1, sword plus 2, whether they were being correctly factored in to your melee accuracy and damage calculations. So I did a little testing and I found out that actually they are. And we can see where it happens. It's right here. Right after you roll the dice, you add your bonus from the gauntlets. Then you add this value from the script to your roll. And this value exactly corresponds to the bonus you get from your weapon, the magical bonus. So plus 1 will add 1 to your roll. Plus 2 will add 2, etc. Now, if we go to melee damage, we can see here it's loading more values from the script. This is for the range of damage. If this were a 6, loaded from here, you would do a dice roll from 1 to 6, for example. This one is flat damage bonus, and this again exactly corresponds to the plus X modifier of your weapon. So we can see that they are being taken, perfectly into consideration. Actually don't have to worry about that aspect, which is good, I think. Now we're at a little bit of a crossroads because I've basically reverse engineered all the stuff that I had wanted to do in the melee accuracy and damage routines. I now have pretty much the full picture, and I'm ready. I'm ready to start work molding the clay and bending this ROM to our will. Now the question is, well, so how do we do this? You've seen me previously, I think in a previous video, I've shown that we can patch instructions in this listing here and then re-export the ROM image. And that's pretty cool because, doing it in here allows me to, code using mnemonics instead of, hex edit, like trying to assemble it by hand, which is good. That's good stuff. But here's the thing. So when I fix some of these routines, I'm going to have to rewrite like a large chunk of the code. I'm going to have to implement a lot of logic that just wasn't in there before. And this is not a good job for patching. Patching is good for replacing single instructions or a couple of instructions, or maybe for, changing the values in some tables. It's very great for those purposes. But for writing like a whole routine, it would be utter trash. Because imagine I write a whole routine and then I realize I missed something. I have to insert an instruction in the middle. That is a horrible experience with the patching, because patching only does overwrite. You can't insert. So I'd have to manually bump all the instructions down. It's just a complete nightmare. So I'm not going to be coding this whole thing using the patching. So that leaves me, okay, so what do I do? Well, I probably want to code, big routines. I would maybe code in assembly, do an external assembly thing, and then import that data into here. Now that brings another question. Where do I put my whole new routines? I have to find some place in memory that's not being used to store my stuff, right? But I don't really know what bytes are being used. Like here, you see, okay, this is probably not instructions. It's just a bunch of gobbledygook. Is it just garbage? Or is it something like maybe graphics? This is where the graphical tiles are stored. And it's probably graphics, right? There's probably not a lot of garbage, I would say. But, the ROM is exactly 1 megabyte, and it's unlikely that they've used the whole megabyte. So there's probably unused space somewhere. Could be at the very end, but not necessarily. But it's just so annoying to try to find these little, code caves to house my routines. And in reality, we don't need to. The beautiful thing is we don't need to. This ROM is only 1 megabyte. But the Genesis, the memory map, you have 4 megabytes that can be mapped to your cartridge ROM. So we're currently only using the first 1 megabyte. We've got 3 megabytes that we could just jam into. And I did some experiments, and it is very easy. There's no problem. If I just add data to the end of the ROM, it'll get loaded by the emulator. It'll run like any other code. So that's beautiful. So we're going to stick our extension into the next megabyte after where the ROM is. We're just going to tack bytes onto the end of the ROM image, and they will be loaded and run like any other. So yeah, we stick our code into here, and then we just patch instructions and we detour from the existing routines to our new routines where necessary. And then when we return, they'll return back to the Wotes ROM, and everything will be hunky-dory. So the next question I had was like, okay, so where can I find, a good assembler, maybe also an IDE that I can use to develop my routines? And I started looking into it, and then I got a little bit of a flash of inspiration. And I thought to myself, do I need to write these routines in assembly? I mean, obviously when I patch the existing code, I'm going to have to work in assembly. So I was kind of stuck in that mode of thought. But then I thought, wait a minute, if I'm writing my own code and if I'm, assembling it, what if I could just compile it? Could I just write C and then compile that to, instructions? machine code just like any other and copy that in? Am I not free to choose what thing I want to use as long as I can find one that targets, my architecture, Motorola 68K? And so I did a little looking into it, and I found the GCC M68K toolchain, M68K ELF. And it's, it's a complete GCC compiler utility collection here. Yeah, it looks like it could be difficult to get it to work on Windows, but luckily I found online, you just do a quick Google search and you can find a pre-built one. You don't even need to install like Cygwin or MSys and run it from there. It's just completely independent, runs on its own. Just download a zip or whatever, extract it, add this binary folder to your path, and you're good to go. And this is freaking beautiful. Now, I'm not, I don't use GCC that often or at all, really. I have used it in the past a little bit in a few cases, but it's not my go-to. It's not my wheelhouse. But, I experimented a little bit on the command line. I could get a CPP file to build, and it output an ELF, which you would expect from the name. It's kind of like an executable container format. Again, I'm not super familiar with it, but I got the general idea. So my next task was, okay, so like how can I take my C code and get it into, a compiled linked form that I can dump into Ghidra and execute on my emulator? So here comes ChatGPT to the rescue. I'm not super familiar with the command line interface with GCC, but I can tell ChatGPT what I want, and we can iterate on it together, and we come up. There's a whole bunch of stuff in here. I'll talk about some of it later, but I say, hey, I don't want an ELF file. I need like just the binary bytes. When this is all done, compiled and linked, I need just a flat binary, nothing else. And so it says, okay, yeah, here's what you need to do. Do this stuff, and then you use object copy, and you can just copy out the actual raw binaries that will be, executed on the CPU. So this text file is a rudimentary first stab at a build process where, I compile, targeting specific processor, and I'm also outputting a list file. Then I link it, which generates an ELF file, executable container. It also generates a map file. We'll talk about that in a little bit, but that is incredibly important for having to detour to my instructions later on. And finally, I use object copy, and that extracts all the useful stuff out of the ELF and discards the husk. Now, after messing around for a while, just on the command line, iterating on these commands and everything, it became very clear to me, I don't want to be building this on the command line every time. That's a pain in the ass. I want a script, and I don't want to edit, a Notepad++. I want a proper IDE. And for this project, I think the best solution is VSCode. So, I installed the required plugins and everything for VSCode. And then I asked ChatGPT, hey, how do I, automate this build process in VSCode? And it said, hey, you gotta make a tasks.json. And so I made my task.json, does a bunch of stuff, but here you can see, here's my compile command. It looks similar to that text file that you saw, the LST, the processor options. And here we have the linker command. And then we have the object copy command. So it's the same sort of thing in a JSON format. And now whenever I think it's like Control-Shift-B, builds it all. Beautiful. Now just to backtrack for a second, I mentioned that when I compile, I have an option here to generate a listing. And so that looks like this. And you can see here, it's an assembly listing of, the code generated. And it's going to be, incredibly useful for verifying that the compiler is, doing exactly what I want it to do. Now, when I execute the linking command, I am generating a map file, and this is essential. So the map file looks like this, and what it tells you basically where all your symbols are going to be located in memory. Now, it would be very annoying if after compiling this, I had to look through, my binary image in a hex editor and try to find where all the functions start in memory. But with a file like this, I can just see, okay, so, thunked melee accuracy bonus starts here. This function starts at this address, and then I can use that directly when editing in Ghidra. Or, better yet, I can add labels in Ghidra, then that give these addresses a, human readable name. Now, by default, when you generate this map file, when you link with just the default options, you're going to get this huge map file that has like hundreds of lines. You're going to get a bunch of stuff that you don't care about, like this exception handling frame stuff. We're not using exceptions, so we're not going to want this. Comment, I don't want this. I don't want this BSS. I want this bullshit. So that is where the linker script comes in. You can tell the linker exactly how you want to arrange your code. You say, hey, discard all this stuff. It's bullshit. I want you to put all my data stuff in the section called data. I want you to put all my text stuff in the section called text. And I have a special section called the Thunk section. We'll talk about that a little later. But I want you to put all my Thunks in here. So I'm outputting from a specific object file. All the stuff from the text section of this object goes into this section of the output binary. And up here I can do some, specification of different memory regions. So I have my ROM region, which starts at 100000, which is the beginning of my extended ROM, the second megabyte, where I'm going to put all my code into. And the length of it is, again, 1 megabyte. And so all of these different sections are going into there. And that is going to help the linker, arrange the addresses and everything exactly as they need to be. Okay, here's where it starts to get real nutty. Of course, I can use my map file, figure out what the addresses are of, my functions or whatever. And then in Ghidra, I can manually add labels, point to those addresses. But I'm a programmer, right? Couldn't I automate this whole process? Could I scrape the symbol data directly from the map file and then, script Ghidra to insert labels programmatically? And so I said, hey, ChatGPT, what do you know about writing Ghidra plugins or scripts? And it turns out it knows quite a bit. And so I said, okay, so I want you to do me a solid. I want you to write a Python program that parses the map file, extracts out the symbols that I'm interested in, builds a table of them, and then adds those symbols to Ghidra, if they aren't existing, and also maybe update the addresses of symbols if they've changed, and remove symbols if they are no longer, in my extension code. And it said, yeah, sure, I'll do that for you right now. Bam! And I got it. And it worked 90% of it worked. The part that didn't work is the part where I said, okay, so for existing symbols, I want you to update their address. It turns out that is not an easy thing to do. And it's just, so I gave up on it. And so I said, okay, so for existing symbols, if the address has changed, well, actually, this comment here just lies because that's not what it does anymore. But anyways, so what I did was I said, okay, so if the address has changed and there are references to it, we just got to print an error saying that, hey, the address has changed for the symbol that you referenced and you got to do something about it because it is not easy to automatically script that change in the scripting language. I haven't found a good way to do it. And that works fine, right? So all new symbols will get automatically added, and symbols that are not used anymore will get automatically removed, and anything else, it'll just flag me and say, hey, there's something here, you gotta look at it. And what this means is that, so let's say I write some C code. Let me just give you an example here. Let's say I'm writing some C code, I write some functions. If I add some more stuff into one of the functions here, in dummy is equal to something, I don't know, just imagine some code in here. All the addresses will be shifted around because new instructions will be, fed in there. And my addresses will change. That'll break references, in my listing. If I have a jump or a branch targeting one of my routines in the extension memory, and those addresses change, that's going to break those. I'm going to have dangling references, and then I got to manually fix them up every time I iterate on my code. That's annoying. So my solution to this problem, since I can't update the instructions and the references in place, is to make sure that my addresses my functions, they don't change their address. So I'm going to use something called a thunk to make that happen. I don't know if this is the correct usage of the term thunk, but that's what I've gone with, so we're stuck with it now. So let's say I have a function here, and this is supposed to be basically called from the existing ROM code. This is my detour function. my routine here. And it's going to do my new melee accuracy bonus calculations. Now, like I said, if I change other code, the entry point, the address of this function will probably change. I don't want that. So I create a thunk function, which is just another function that I'm going to put at the very top of the image file. And all it does is it calls into my function. And I'm going to have one thunk for every entry point. And if I do things like this, my thunks all have the same implementation. It never changes. It only calls the real function. So their addresses will be incredibly stable. You know, no matter how I change the implementations in here, add more code, remove more code, these thunks will all remain the same length. They will all have, you know, stable entry point addresses. I'm going to make sure that the target of the thunk is declared as no inline, so it doesn't just jam the code in here and screw up my thunks. But besides that, it's very simple. And so as I build these entry points, I'm going to have like a whole list of thunks in here. If I ever decide I don't need an entry point, I change my mind, I wouldn't just delete it outright, because that would shift all the other ones up. I would have to keep it around, but just leave it unused. And the next time I wanted to add a new entry point, I would replace the one that I'm not using anymore rather than add to the end, is basically the way it works. And again, it'll be a little bit of busy work to keep these thunks in sync with my extension code. So what did I do? I got ChatGPT to write me another script. And all it does is it scrapes my extension file. It looks for this symbol here, exported, which is just an empty macro define. It doesn't do anything except that when my Python script sees it, it is going to read that in and use all of those, collect all of the exported function signatures and use that to generate thunks.cpp. So this is a generated source file based on my extension.cpp. And then in my build script, you can see here, I have two compile steps. You know, compile the extension thunks and compile the extension implementation. So those go to two separate object files, and then they get linked together into a single binary. And based on my linker script, the thunk will always be at the very top. So it will not be pushed around based on, you know, if my implementations change size, they won't affect this at all. And now I have my nice stable addresses. So in my listing file now, when I make references to my extension code, I won't have to worry about them being dangling, you know, in the future. And if by some, you know, strange reason I screw it up and they do dangle, this script should point it out for me and say, hey, you got some address change that shouldn't have changed, those thunks, you gotta look into that and fix it. So yeah, and this script, by the way, the one that imports the symbols, it also updates the actual image data, the binary image. So the first time, let me just show you. First time you compile and build, you get this extension full. I have to manually add that to the Ghidra program. But after that first manually adding, every time I run the script, it'll update the binary data automatically. Very nice. I'm going to tell you, ChatGPT did a lot of heavy lifting on this aspect of it. I would have given up without it, I think. I would have just been like, this isn't worth it. But with ChatGPT, it made it viable for me to create all this automation. Working with systems that I'm not familiar with, like working with Ghidra's API, or even just working with Python. I mean, I'm not that good of a Python programmer. I would have probably just said, screw it, I'll just manually do it every time. But yeah, there you have it. There is my whole crazy system that we've got set up here. And I hope you're excited for the next video when we're actually going to start modifying the game code in like a real significant manner. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button. It helps a lot. And I will see you again with some more ROM hacking.